Okay, so this is week 3, and we're trying to cover chapter 3. In this chapter, we will get exposed to some of the steam system fittings, mainly safety fittings, which include relief valves and gauges. So the objective this week is to explain the purpose of safety valves and describe how they work. We will talk about steam pressure gauges and explain common consideration for their use. What kind of gauges do we have? How are they used and where are they placed and how do we calibrate them? Explain the purpose of how do we remove a steam separator. How does it work? How do we separate steam from water and also from air? Also, we talk about boiler stop valves and describe methods of removing air from the boiler. So we want to separate air, steam, and water in a steam system. So these are some of the most common fittings you'll see in a boiler. Steam gauges, shut-off valves. Shut-off valves are placed right before the gauges in case we need to replace them or calibrate them. Safety valves, usually we have more than one for redundancy. Safety valves are very important because it's our first defense against buildup of high pressure. Vents to let out all the air if we have any kind of air buildup. Gauges, these are called the water column, where it shows you what is the water level. Probably you've seen those in steel balls for residential. And also a side glass to see the water level inside the drum. And here we have the bottom blow down valve. What is the blow down valve? What is blow down? Blow down is when we try to get rid of all the sediments and accumulation inside the bottom of the tank, maybe rust or sediments. So after each cycle, and usually we go by the manufacturer or the plant recommendation, we open the blow down valve and we let out all the water. Here we see the piping layout for safety valve that will allow for proper drainage of condensate. So we have our condensate because again we will have steam, water, and air. So the safety valve here will allow for the drainage of water, and we will also have safety for the pressure buildup. So safety blow-down valves is a drop in pressure between popping pressure and reseating pressure as a safety valve relief boiler overpressure. So what does that mean? So if you ever been exposed to a safety relief valve, you will notice that there is a popping pressure. We want the valve to become very fast acting. So once you build the pressure, it will pop quickly at that pressure and let out all the excess steam pressure out. Then the seating pressure is when it starts to go down and seal again the system. So this is the blow down. So when we open up the blow down pressure, we have this double pressure. This is the cutoff point, and then you see how it slows down to the seating position. So reseating is when the valve is closed, and the popping pressure is when it immediately opens up for excess pressure. This is a safety relief valve. Safety relief valve again is very, very important component because it prevents us from building any kind of pressure. If you look at the components here, probably you will see this in your study guide. The book tries to let you remember all those components. So we have a lever for manual operation, but the valve should be able to operate by itself without any kind of lever. And here is the spring. The spring is gauged to resist an opening at certain pressure, and these springs get calibrated periodically. Usually there's a tag that tells you when was the valve serviced and when is the next service period. And the pressure exerted on those little seat is what we are trying to accommodate here by the spring force. To simplify the concept, we are basically exerting force equal to the pressure that we want to have inside the pipes. If this pressure is increased, then it will overcome the spring force and it will open up the valve. And again, it will pop right away, let the pressure out, then it will get reseated. This is basically the steps and how does it work for seating and reseating. You can look at it in the book with more details. So manual testing is how we usually test the valve, and we want to see it popping right away. So it's not always the common practice for testing all real valves, but this is one of the ways to do it. However, they have to be periodically tested and calibrated, because if you think about it, over time and heat, it will build some rust and it will resist movement. So if we pop the relief valve and it does not sit quickly and correctly and is still leaking, and we need to be reserviced. And if you notice, we have two of them, so usually we have two. And if you look closely, there's a tag that shows when was it tested and when it's supposed to be calibrated. Again, this is the code. The code required, we have a plate with the relief valve number, the testing, when are the parts supposed to be changed, or the spring over time will lose its K factor. The K factor is the material property that allows it to have the proper amount of stiffness and the proper amount of force that will be exerted against the seat. So every relief valve should have a name plate on it, and it should be tested and tagged periodically. These are fusible plugs. It's again a second kind of way to protect us from having excess pressure. Why are they called fused? Why are they fusible? Because they can be used it's like a fuse. If we ever see an electrical fuse, probably you've seen that it has a piece of metal that melts and drops. So these plugs usually have some kind of material inside that at certain temperature and pressure, they will pop out, and the only way to replace that is to replace the entire plug. So it's a secondary way to counteract accumulation of pressure inside the system. So we have a relief valve and we have some fusible plugs. The Bourdon tube and adjustable linkage, basically it's a way to adjust for pressure. So when you have slight increase in pressure, the Bourdon tube will accommodate for that and without some pressure, but then will go the right level. The steam siphon protects the Bourdon tube from high temperature of steam. So I don't think that they are very common these days, but you will see them sometimes in some plants. And the reason that we have this lube is to prevent the Bourdon tube from being exposed to high increase in pressure and fluctuation inside the system. Here's the interesting concept that we need to know, which is what is the difference between absolute pressure and gauge pressure. You will get exposed to that a lot. So absolute pressure is the pressure without the atmospheric pressure, and gauge pressure is whatever you see on the gauge. So atmospheric pressure usually is 0 psi. If you notice here is the gauge, it's going to be 0, but the average or the most common atmospheric pressure is 14.7 psi. Psi is pound per square inch. So if you see PSIA, that's pound per square inch atmospheric, which is pound per square inch gauge. So gauge is what it reads. So 0 gauge is, if you think about it, if you have a gauge, the gauge is showing you 0. It's not actually 0. There is pressure on it now, which is the absolute pressure. So this is the difference. Anything below that will be vacuum. So anything below 0 is vacuum, 0 gauge is vacuum. And the absolute vacuum, perfect vacuum, is 30 inches Hg, which is mercury, or 0 psi. I don't think it's completely 30, it's 29.9 something, but this is the difference between gauge and pressure. So if we were to calculate absolute pressure, or gauge pressure, plus 14.7. That will give you absolute pressure. So there's so many ways to calculate and calibrate the gauge pressure. The reason we need to know that is periodically you have to test your gauge. Let me see if I have some gauges in here. Couldn't find any, but anyway, the gauge pressure usually have to be calibrated periodically, and that depends on the manufacturer and the recommendation. And even the electronic ones has to be gauged. Because if you think about it, what is happening inside a gauge pressure? If we look at it, if this is my tube that is connected to a bigger gauge, there's a membrane here, very thin piece of metal sometimes, that reacts as the pressure is acting against it, and that in turn will move a needle back and forth. So those mechanics, after a while, they are subjected to a lot of wear and tear. So they do change, and we have to keep recalibrating and sometimes even replace the entire gauge. So this is the pressure gauge here, and again, sometimes we have more than one gauge in the same location just to verify our pressure. More pictures of gauges, steam them out. We don't have to really go too much into cyclone separators. But what they do, cyclone separator actually, what they do is they send the steam through a circular drum in a spiral motion to remove moisture from the steam. What do they mean by that? How do we remove moisture from the steam? Well, steam is moisture, isn't it? But the idea is to separate water, liquid water from steam, and keep the steam as complete gaseous state. So that's what the cyclone does. It spirals very quickly to use centrifugal force to push the water on the sides and keep the steam by itself in gaseous state. The main steam, again, even though we have a lot of valves and automated valves, we always have to have a manual override. So this big valve over here will close the main steam line. You see how huge this pipe is, and how can we keep it closed and open. And this is the main steam valve controls in the top, because it's going to be in top of the boiler, and that's why we have a chain going through it. There's a lot of automation when it comes to valves, and those valves are automated using a motor. They put a motor on top of it and can control the opening, whether it's half open or half closed or completely open or completely closed. This one is manual here, but sometimes you see a manual override, and also you can see ones that are automatically opened and closed. Expansion vents are very important for the steam line, and why is that? Why do we need some kind of expansion vents? What they do is, of course, metal do expand with heat, and if we don't allow it flexible, if we don't give it a lot of slack to bend comfortably within design, it might break. Again, we're going through a lot of cycling back and forth, so we would like to have some kind of bends in lines that we predict that will expand and contract a lot. So we put some bends to allow the metal to comfortably go back and forth. Vents, again, usually it's on top of the piping configuration, and the vents are always open to let out some air, and whenever you fill with water, if water comes in, something has to come out, and usually it's air, so you're always going to have a vent open whenever you add some water. So these are some of the basic fittings we have. If we can just recap that, what did we talk about? Air separator, relief valves, RVs, and air vent. And what else do we have? This is the main ones that we want to think about. And also fusible valves. The book, let me just go over the book. Yeah, the book does a really good job in trying to calculate those valves. Don't worry too much about the calculation. I'm calculating with the seats. This is, I don't think this information is very important at this point. But if you can just identify the types of valves available, and that's enough. For the applied math portion that I want you to know, which I feel it's important, is how do we calculate the hydrostatic pressure. What is hydrostatic pressure? Hydrostatic pressure is the weight of the water which will exert at some point pressure on a tube. So if we think of water as a column, so I always use this example that if we have a big tank, small tank, a different shaped tank, and we have a point here, and this is the same height. And we'd like to know what is the pressure at these points, 1, 2, and 3. It's a trick question. Everybody will think maybe it's the pressure at vessel 3 is more than 2, but they are all the same. They all have the same pressure because especially if the water is filled at the same, if they are all fell at the same level. So we have the same height from the top, and the same height. Actually, the height from the bottom does not matter as much. Most of the height from the top. The height from the top does not matter at all. So it's the level from the top to the bottom is what matters for the pressure. So how do we calculate the water pressure based on this concept? So the water pressure which is hydrostatic pressure, which means if the water is still in a tank or in a pipe, so water pressure will equal rho GH. Rho G is the density of water. G is the acceleration of gravity. And H is the height of water. So we don't have to remember those two numbers that have been given to us, and this number in imperial units is 0.433. So we can say here it's the static pressure is 0.433 times the height of the water at any point. So if we would like to know what is the pressure at this point, since it's really far by 20 feet from the top to the bottom, you just multiply 20 by this number, and this number is going to be always constant for water. It's only water. Of course, if we use something beside water, we have to change the number, but that's something we can always look up. So this is how we calculate hydrostatic pressure in a simple manner. We don't complicate things. Just basically multiply 0.433 by vertical feet. Please try to read chapter 3 and go over the questions in the back of chapter 3 in the book and also in the study guide. Thank you.